All right, good morning, everybody. Welcome back to your favorite class. Yes! All right, today you're going to get to do your first lab. Do your first lab. All right. A couple of announcements before we dive in on what's going to happen today. First is that your first homework for the class is due tomorrow. Um, and that should come as no surprise. I had a lot of questions at office hours this morning, which is nice. Um, so much so I got kind of a little bit behind. So try to get to everybody. Sorry if I missed you. I'll be around my office most of the day today if you have questions. So please ping me on Teams, and I'll do my best to sort of get to you and hopefully answer your questions about what's going on. All right. So I want to talk about a little bit about what's going to happen today. So like I said, the lab periods are going to kind of vary from week to week. But today what we're going to do is we're going to sort of do our first lab for the class, and that is the combined loading lab. So if you haven't already done so, there's a number of pieces of information on Blackboard related to this particular lab that will be helpful. The first is the lab handout for this lab, and I've taken a lot of time for this particular lab handout specifically this year because I'm going to give you a pre-recorded video of me performing the lab experiment, and I wanted to make sure that I gave you guys a handout that was like pretty clear, sort of step by step in the handout of all the things that I was doing in the video. So I think the lab handout does a pretty good job of like explaining what you're going to be doing in this lab. It shows pictures of the apparatus. It has like a step-by-step list of exactly what I'm doing in the video. And even in the video, I'm kind of like, all right, now we're on to step 12. Now we're on to step 13. And it just kind of like goes sort of hand in hand with that procedure. So please take a look at that procedure. Sort of prior to watching the video, make sure you're familiar with it, and maybe you want to follow along with it in the video. I'm going to show that here in just a second as well, so we kind of like reinforcement. The second thing for this particular week is we're going to be using strain gauges to calculate strains at various points on our structure in this lab. And we haven't really talked about strain gauges much, and I don't know how much you talked about them in 2004. So we need to have like a maybe 20 or so minute lecture on strain gauges, how they work, what they are, and how we're sort of going to use them for this lab to sort of determine where the strain is and what the strain is at various points on our piece, given applied loads that we might put onto our structure. Okay? So the last thing that's listed there in that folder on Blackboard for this lab is the video of me performing the lab. So that should be kind of like the last thing that you do is kind of go to that video and work through the video. So the video is just me doing the experiment, and you'll see everything that's going on there. But you should have like at least read through the lab report or the lab handout document before you sort of go to that video. So I just want to pull up that document quickly here for everyone to sort of look at, and I just wanted to talk about this quickly and sort of talk through the lab and what's going to happen in the lab before I sort of release the video to you and have like kind of our strain lecture. So I'm going to share my screen here, and I'll bring up here this what is the handout for this particular lab. So here's your handout, and the objectives here that we're going to be after today for this particular lab is we want to calculate stress at prescribed points in a beam under a known state of combined loading. And I just want to pull back one more time to my actual camera and show the apparatus for the lecture. So the camera kind of should be on me at this point, but here's the apparatus that we're going to be using today. This is like a circular aluminum rod that would normally be sitting on a table with this particular base here. The idea is it sits on a table, and we sort of like put loads on this end that will sort of induce like stresses on this end of the beam. All right, and I'll come back and show this apparatus a little bit more in detail, but there's a good picture of it in your lab handout if you want to take a look sort of down here. So this is the apparatus that we're going to kind of be using for this particular lab. And we're going to be applying loads to this structure in a variety of different ways that will induce stresses and strains at points of interest. Particularly, we have like one point on the top here, point A, and 2 points on the side, which we call point B and point C. And we're going to be measuring the strains at those points on this particular piece as we load up this apparatus. So we have load on this piece, and that's going to induce strain at A, B, and C. And using the strain values that you calculate in this lab, you can determine what the stress is, and you're going to see how the experimental stresses that we get from this lab compare to theoretical stress values that you might calculate using the combined loading equations that you're doing for your homework now and that we've done in lecture the last couple of days. Okay? So you're going to calculate stress states at prescribed points in the beam under a known state of combined loading. So what I mean by that is I'm going to prescribe this is the load we're doing, and you can calculate what the stresses are at those points of interest. Then you're going to take these calculated stress states and sort of look at the strains that are occurring there to calculate what the modulus for this might be using Hooke's law. So Hooke's law, remember, is something like the stress is equal to the strain times the modulus. And we'll talk a little bit more about Hooke's law in my strain gauge lecture in just a second here. So these are the things that we're going to be after today, and I just want to make that clear. Another thing I want to talk about is what is your actual deliverable for this particular lab. And since this is the first time that you're going to be sort of writing a lab report, I want to give you the chance to get some feedback for me on your writing for free. All right, full free, $0. All right, and the way that I'm going to do this is I'm going to ask you guys to submit sort of the first draft or the rough draft of your particular lab report by next Wednesday class time. All right, so that's one day before we normally meet for lab. It's next Wednesday at 10 a.m. So I have that pretty clearly described right here. Your rough draft due then. The whole purpose of this is I'm going to take all of your lab reports that you submit on Wednesday, and I'm going to read each of them Wednesday night and provide each of you some pretty thorough feedback on your writing. Then on Thursday next week during the lab period, we will meet one-on-one with like 5-minute meetings. So I'm going to ask you guys to sign up for like 5-minute meetings with me where we'll meet on Teams virtually, and I'll talk about, okay, this is your writing. These are things I think you can do to improve your writing and sort of get you to the next level. All right. And this is all sort of like ungraded. All right. It's just the first step in getting you guys to like make and write good lab reports. I told you, you're going to be good writers by the end of this. All right. Rawr. All right. Then after I give you back your comments, which are be sort of 1 week from today, you'll have one more additional week to turn in your final report. All right. So 2 weeks from today, you will turn in your final report for this particular lab. All right. So I think that will be the 31st. Or the 1st of October, sorry. So hopefully that is all clear. Now, like I said, for this particular handout, it goes in gory detail about all the stuff that we're going to do in this upcoming lab, including the equipment that you have, so on and so forth. And we have a pretty exhaustive like procedure here that you can follow along with me in the video as you go. Okay. So here's the procedure, get all the equipment, measure all the stuff. We talk about strain gauges, how to hook them up, so on and so forth. Okay, so you can sort of like go through this procedure, and I would urge you to sort of like read all of this procedure sort of before you dive in on the lab video. Okay. All right. So that's the handout. The next thing I want to do is I want to talk about the strain gauges themselves. And I'm going to put you back on the main video here again, looking at me, and I'm going to bring the apparatus in here again. So you saw a picture of it. Here it is again in action. We're going to later put like a steel through rod through this portion and sort of hang it off the side. It's not in there right now, but we will include that later. And I want to talk about where the critical points of interest are on this particular bar. So we're going to do some things with load on this end, and that's going to induce a variety of stresses kind of on this side of the beam over here. And so you'll notice that we've strategically put these gauges on our apparatus. And so hopefully you can at least sort of see that a little bit. This sort of like brown looking piece of Kapton tape, there's actually like a gauge here. And the gauge is more or less like a resistor that's going to measure the resistance of a wire that's inside of that Kapton tape during this process. And what's going to happen is when we load this particular structure, it's going to change the resistance of the wire in that gauge in some appropriate way. And the change in resistance of that gauge will correlate to a known amount of stretch in the bar or a known amount of strain in the bar. Using the known amount of strain that we get from the experiment, you can then multiply by modulus to get the stress, for instance. Okay, so here's like a singular gauge on the top, and you see that it's sort of wired there with like a red and a white and a black lead wire. All right, we have additional strain gauges on the side, so hopefully we see that there's a series of strain gauges here on the side of the bar. We have 3 gauges there on the side of the bar, and also on the back side of the bar, which you can't really see from your angle here, but on the back side of the bar, there are 3 additional gauges. And so this would correspond to like point A, point B, and point C in the figure of your lab handout. So I just want to make this like perfectly crystal clear. I know I'm kind of beating this to death, but I'm trying to make it as clear as I can. So we have this singular gauge on the top, which I was showing here at point A. We have 3 gauges on this side and 3 gauges on the other side. Okay, so with that in mind, let's now start in on what I would consider kind of like the lecture portion of this lab. And I'm going to use the time here to give a lecture on strain gauges. Okay, so these PowerPoint notes are available on Blackboard, and if you want to follow along like with these notes in kind of like the traditional lecture manner, I would sort of encourage you to do that. So I've just got to talk about strain gauges for maybe 20 minutes, just so you understand how they work and why we're using them. All right, so let's go ahead and do that. Let me get my coffee here. It's kind of warm in here. And by coffee, I mean there's cherry Coke in this mug, but it looks like a coffee mug, so I'm confused. All right, so let's talk about strain gauges. So strain gauges are useful in mechanics in that you can apply them to a structure, and it tells you more or less what is the strain on this particular piece right at the surface. So let's do a definition here of strain gauges. And it's going to be a device that's used to measure strain. On a material surface. So you saw that those strain gauges that we had on that aluminum member over there were on the surface of the bar. So that's going to measure the strain directly on the surface. All right. Now, we know that strain is non-uniform inside of our piece, and it's going to be different on the surface than it is inside of the piece. So a limitation of strain gauges is that they can really only measure the strain that's happening on the surface of the piece. Now, there are many types of strain gauges, but the most common, and the one that we're going to use in this particular lab, is what's known as a foil strain gauge. All right. And the way that a foil strain gauge works, I sort of talked about this already, is basically it's a conductive wire in an insulating housing. All right. So if you wanted a picture of this, what this kind of looks like, and you sort of saw this on the surface of the aluminum member, it looks a little bit like this. So the idea here is that these like red bits are the conductive wire, and this yellow bit here is the insulating housing. Right? And then we have like leads that are coming off here. Right? And so these are going to, let's say those leads are going to an ohm meter that will help you monitor the resistance of this gauge. Right? Now, that wire is sort of like coiled back and forth like this with a certain directionality, and there's a very specific reason why it is sort of like coiled in that manner. And that's because the resistance of this wire, if you might have learned this in sort of like your circuits class, or I don't know if you maybe learned this in 1601. Is that the instrumentation class or is that 1301? I always get those confused. But you would know that the resistance in a wire is given by the following equation. It's going to be the resistivity of the material, so that's rho, times the length of the wire, L, divided by the cross-sectional area, A. So let's define these. R is the resistance. Rho is the resistivity. And this is a material property. So the resistivity of the material, let's say your lead wire is made of copper or tin or something else. Whatever that material is that the wire is actually made of has a material property known as a resistivity. L here is the length of the wire. And then A is the cross-sectional area of the wire. All right. So how is this useful for actually giving us strain? Okay, well, we know strain has to do with like the change in length of an object over its original length. So let's just do a recall. Like 1D strain is given by the definition epsilon is something like delta on L. All right, where epsilon is the strain, delta is the displacement. So how much it's like moved, and then L is the original length. All right, so something that has a strain reading of like 0.01 has elongated 1%. All right, so maybe if it was originally 1 meter in length, now it's 1.01 meters. All right, that would be like an example. Right. So how do we go from a gauge that's on the surface to strain? Okay, well, let's talk about then how this actually works by looking at what's going to happen if this gauge is stuck onto the surface of a piece and we either pull that piece or compress that piece. So gauge functionality here. How is this actually going to work? All right. Well, as this gauge is like elongated or compressed, you're going to change the resistance of that wire that's inside the gauge. So as it elongates or compresses, the resistance will change. And the idea here is that if we elongate, like the length of the wire that's there is going to get longer. Okay. So as you elongate, the wire will increase in length. So the idea there is that as L goes up, if we look at how the resistance would change given an increase in L, we go back to our equation here that tells us how resistance is governed. Well, L and R have a direct relationship with each other. So if the length of the wire inside of the gauge increases, the resistance will also increase accordingly. All right, so as L goes up, that means that the resistance will go up inside of my gauge. Also, when you elongate, the cross section is going to have to shrink as I pull this by Poisson effect. All right, so cross section of wire will decrease. And that's kind of like by Poisson effect, right? Like as I elongate something to maintain the total volume of that structure, sort of the sides have to collapse so that as you pull on it, the edges are kind of coming in. So the idea there then is that as the cross section goes down, what is the relationship to the resistance? Well, if we go back to our equation here, resistance is inversely proportional to changes in the area, meaning that if the area goes down, the resistance will go up. So again, as area goes down, that's going to lead to increases in resistance. So the general idea is that as we elongate, the resistance will generally go up, right? Very similar idea for compression. So the wire will get shorter. And as the length goes down, the resistance will also go down, direct relationship. And the cross-sectional area will increase. Again, as A increases, the resistance will decrease, an inverse relationship. And so what this looks like, and I have a nice sort of picture of this in the notes for clarity's sake, is that when you have the strain gauge on the surface of a material, it might look something like this. It's going to sort of adhere to the rules that I just talked about. When you first place it on the surface, it's not really like strained in any way. It's, let's say, unstrained or in some reference configuration. But then as we elongate, okay, so here we're in tension, sort of we're pulling it or elongating it, then the cross-sectional area of the wires themselves, so here are the individual wires sort of in this long pattern, the wires themselves will decrease in area and will increase in length. So what that means is that the resistance is generally going to increase, as we sort of described above. Right? When you're in compression, these wires get thicker, okay, by Poisson effect, and the length decreases. So all that means that the resistance is going to decrease of this wire generally. All right. Now, how do we correlate changes in resistance to the strain measurement? Well, that all just comes down to the way that the strain gauge is manufactured. Every time that a company makes a strain gauge, they have to know, all right, if I made it in this way, they have to take that strain gauge and basically put it onto a bar, give it a known stretch, and say, all right, if it strains 1%, my change in resistance is this. If it strains 2%, my change in resistance is this, 3% this. And they basically come up with a calibration factor for how much resistance change there is per strain that is induced inside that piece. So when you buy a strain gauge from a company, they have to tell you what that calibration factor is, okay? That calibration factor that tells you the amount of strain per change in resistance of the gauge is known as the gauge factor. Okay, so this is like a manufacturer calibrated data. That tells the change in resistance per strain applied. Right? The general formula for gauge factor, GF, gluten-free, no, I'm just kidding, gauge factor, would be the change in resistance divided by the original resistance per incremental strain that you apply. So how much does the resistance change relative to the original resistance per increment of strain that you apply? Okay, so here GF is gluten-free. No, gauge factor. Delta R is the change in resistance. So this change in resistance is induced by, loading the piece. R is the original gauge resistance. And then epsilon is your strain. Okay. So companies will do this. They'll put a strain gauge onto an aluminum bar, pull it a little bit, a known value, and say, all right, the change in resistance was this amount. So that tells me that the gauge factor is this value, right? if you want to calculate strain given a known gauge factor, then you just rearrange this equation to strain is equal to the change in resistance divided by the resistance over the gauge factor. So each one of these apparatuses for the lab, and I'll come back to the notes in just a second. I want to pull up the picture just a second. Each one of these apparatuses for the lab has the strain gauges that are kind of like applied there. So you see that Kapton tape strain gauge that you see there. We need to know what the gauge factor is of that strain gauge so that we can do the calculation appropriately to determine what the strain is at that point with some change in resistance that we're going to measure during the lab. And so you see sort of like taped on the bottom here, maybe you can't see it with the glare, but taped on the bottom there is a little piece of tape that someone who made this apparatus placed on here that tells us that the gauge factor for this particular lab in each one of the gauges is 2.11. It'd be hard to read. It's like a little bit broken off there, but maybe you can read there that the gauge factor 2.11 for all of the gauges in this particular lab. So it's important for us to know that so that we get the appropriate strain measurements when we're actually going to convert from changes in resistance to strain measurements directly. Okay, so hopefully that's clear, sort of how these strain gauges work and how they operate. All right. Now, in the video, you'll see us put some loads on the structure, and we're going to be reading the strain gauges with some strain indicator boxes. So we're going to wire these strain gauges to a box, and we're going to then read the strains from that particular box. So you'll see that in the video. All right. Now, in this lab, you've got a variety of different strain gauges that are applied. And what you'll notice is I've only really talked about a singular gauge up till now. All right. But a singular gauge can really only give you the strain in one direction. All right. So I'll title this section Measuring Strain in Multiple Directions. All right. So the idea here is that one gauge gives strain in one direction. One Direction's funny. It makes me think of the musical group, One Direction. I still don't know if they even exist anymore or not. Like, did they break up? I mean, I feel like One Direction had like a falling out, and you know, John or whatever his name is, I don't know, whatever his name is in One Direction got mad and went for a solo career or something. Do they still exist? I don't even know if One Direction still exists. But anyway, if you have a singular gauge, it measures the strain in one direction. So if I sort of espouse on that a little bit, let's say we have one singular gauge here. Am I getting information? Jeremy knows. Of course Jeremy knows. Oh, can you share screen again? I'm sorry about that. So measure strain in multiple directions. So one gauge would give strain in one direction. And so let's say we have sort of the leads coming off here for this particular gauge, and we've got the wire inside of the gauge that's sort of like moving back and forth like this inside of the gauge. So generally, if you applied this gauge to the surface of a piece, yeah, it could measure, and we say like XY. This gauge by itself would give you what is like the strain in the X direction, right? There are, you know, points where you might want the strain not just in a singular direction, like the X direction, but you also might want to have the strain in, let's say, the Y direction, or you might want to have the shear strain, okay? So if multiple strains are required at a single point, you need multiple gauges. All right. So like, let's say this was a point of interest on my structure. I don't know, let's call it point A. Well, maybe I need one gauge that like runs this way to give me like epsilon x, and maybe I need another gauge that sort of like runs this way to give me like epsilon y. All right. So that's an example of having multiple gauges at a singular point to give us multiple strains. Okay. So we may need multiple gauges. At a single point to define full strain state. I'll say full 2D strain state. Let's say epsilon x, epsilon y, and what is the shear strain, gamma xy. So special gauges that have like multiple individual singular gauges on them at one particular location are called strain gauge rosettes. So, strain gauge rosettes. Strain gauge rosettes are basically gauges that you can purchase that actually have like 3 gauges on them. All right. These are strain gauges that are aligned to give readings in multiple directions. All right. So let's say I have a point of interest, I don't know, let's call it point O, and we have a coordinate system here that's something like x, y. Right? There exist purchasable items called strain gauge rosettes that have the gauges aligned in some particular fashion. The most common strain gauge rosette is known as a 45-degree, I'm putting this in quotes, rosette. And a 45-degree rosette has 3 strain gauges that are aligned at 45-degree angles. So the idea here is that you have one strain gauge rosette that might be all contained in one piece of kapton. Let's say it's all contained in one piece of insulating housing. And you have one set of leads that like starts here and does this sort of thing. Okay? And maybe this is like resistor number 1. And maybe you have one over here inside of this insulating housing. That's like resistor number 2. And maybe you have one more that's at like a 45-degree angle here. As well. All right. So within one sort of gauge, you actually have like 3 gauges. All right. And say this would give you like one strain gauge reading. This would give you like a second strain reading. And this would give you like a third strain reading. All right. So the benefit of these like 3 gauges in one is that you get strain in all 3 directions. And it's pretty easy to see here that in this situation, the strain along the x direction is simply going to be whatever strain is read by this first gauge, all right? The wire associated with like epsilon 1. It's also pretty easy to see that the strain in the x direction, or the strain in the y direction at this particular point, is going to be epsilon 3, since it's gauge number 3 that's sort of like reading along that direction. Now, the special thing about strain rosettes is that they can give you the shear strain at this point as well. And in this particular situation, the shear strain, gamma xy, is going to be a combination of what's read at this like 45-degree angle and also like the two x and y directions. So in this particular situation, the shear strain is actually 2 times the reading of gauge number 2 minus the reading of gauge number 1 plus the reading of gauge number 3. And this is an important equation that we're actually going to revisit a little bit later. You'll see this one pop back up later in the course. Now, why is that important for us? Okay, so in this lab, there are 45-degree rosettes at points B and C on the structure. Right? And so you'll need to calculate the shear strain at point B and the shear strain at point C using the equation above. Now I want to bring the camera back one more time and show this structure and actually show the strain gauge rosette on the structure that would be at what would be like point B or point C. Right? So I'm going to put this back onto me, and I'll bring the structure in one more time. And you'll see here that on the side of the bar here, it's a little bit difficult to see, but you have one piece of insulating housing, which is this like large brown Kapton piece. But inside of there, there's actually 3 gauges. And those 3 gauges are aligned at 45 degrees with each other. So you can sort of see like the lead wires that are running to each of the 3 gauges. And there's one gauge that runs along the axis. Let's see if I can get a pencil in here to sort of help me with this. There's one gauge that sort of like runs along the axis, like this general direction. There's one gauge that runs like at a 45-degree downward this way. And there's one that runs at like a 45-degree angle sort of upwards this way. So I'll bring it in one more time. Maybe we can sort of take a look. And it's a little bit difficult to see, but maybe like the shining light of my office light will sort of show those 3 gauges and the 45 degrees at which they are respective to each other. Okay. In the video, we also zoom in on that gauge, and you can sort of see it a little bit more clearly in the video. All right. Now, one last thing I want to talk about is Hooke's law, because you'll also need that for this lab. And I will share my writing pad again. All right. So the last thing we have to talk about is Hooke's law. And you definitely should have talked about this in 2004, so this should generally be review. Hooke's law is a law that relates stress and strain through a material property known as the modulus, right? This is relates stress and strain through material properties. Specifically, those material properties of interest that we care about are elastic modulus and shear modulus. So your one-dimensional Hooke's law, which would be useful if you have like a singular gauge that gives you the strain in one direction, might look something like the stress is equal to the modulus times the strain. Right? Well, 2D Hooke's law is going to be the relationship between shear stress and shear strain. So here, tau is equal to G times gamma, where E is the elastic modulus and G is the shear modulus. Now, in this particular lab, what you're going to do is you'll see an experiment, all right, where in the experiment, you'll see strain values epsilon, and you'll see strain values which allow you to calculate gamma. These are gotten by experiment. Okay? Using the loads that are applied on the structure, you can calculate what the stress would be at those particular points. Okay? So these are gotten from calculation. Right? Specifically like the combined loading calculations, it will look very similar to the combined loading calculations you just did from the homework. So the idea is that you can calculate what the stresses are at that point from combined loading equations. You have strain measurements from the video, and that will allow you to calculate these terms. All right, so I'll say here, combined loading calculation. And these are calculated from Hooke's law. So that's the whole purpose of the lab that's going to happen today. You'll get strain measurements from the lab. You'll have stresses that you can calculate from sort of theoretical combined loading background. And you marry those two things together with Hooke's law to predict what is the elastic modulus and the shear modulus of the bar. Then you're going to report things like the error in your calculation and compare it to what are known values of shear and elastic modulus for aluminum and all that yummy good stuff. Okay. Are there any questions? That's kind of it for the lecture at this point. Talked about strain gauges, talked about how we can use strain to get stresses through Hooke's law. I sort of showed you as much as I could of the apparatus here. We ran you down through the procedure about like kind of what's going to happen. That's really all I have prepared for the live portion of the lab today. I would encourage you at this point then to sort of like double check and make sure you like understand the procedure that I sort of handed out. And then when you're ready, go to the YouTube page, go take the link from Blackboard to the YouTube page that has the lab video and go ahead and watch the lab video. I'm going to stay here in the Microsoft team meetings, and I'll be here for questions if you have questions about the video over the next hour, or if you have questions about the lab in the next hour. Otherwise, that's it for me in terms of the live portion of the lecture right now. So I'll leave you guys here. I'm going to turn my camera off and my mic off. If you have questions, pop them up in the chat, and I'll respond as they come up. Otherwise, I'll share the link to the video and take the time now to watch it. Okay, see you guys later.